Today we are discussing the formation of the O2 minus 2. Any molecular ion formation, if we have to discuss, then two approaches are there. The first approach, we can consider the formation of molecule, say here O2 molecule. And in that molecule we will add electron if charge on the molecular ion is negative, or we can remove the electron if charge on the molecular ion is positive. Here O2 minus 2 is a charge, so in oxygen molecule I have to add 2 electrons. With the help of that I can explain the formation of O2 minus 2. And other way, combining species I will choose in such a way that O2 minus 2 will be the result. Means I can consider one where atomic orbitals of oxygen, they are energetics, and other where ionic orbitals of O minus 2. If electron number changes, then energetics of the orbitals also changes, because number of protons are remaining same. Hold of the nucleus on the electron will be different. If it is different, then energy will change. So let us see energy levels of oxygen, energy levels of O minus 2 to result various molecular orbitals.
Three compartments are shown in the MO diagram. Left compartment is atomic orbitals of oxygen. Middle compartment, molecular orbitals of our species, peroxide ion O2 minus 2. And right compartment, the ion that I want to consider which can combine with oxygen atom, that's the O minus 2 ion, oxo ion. Electronic configuration of oxygen 1s2, 2s2, 2p4. In this diagram, 1s orbital is not represented because it is an inner orbital, and during formation of molecule or molecular ion, outer orbitals only will take part in overlapping, in interaction. So 1s orbital, inner orbital will remain non-bonding. As is the case for oxygen, same will be the case for O minus 2. But I want to ask you the one question. 1s orbital of oxygen and 1s orbital of O minus 2, will they be of the same energy? No. Why? Number of protons are the same both where. 8 protons are there in oxygen, 8 protons are there in O minus 2. But number of electrons are different. In oxygen, 8 electrons are there, and in O minus 2, that's oxo ion, how many are there? 10. Means 8 protons are attracting 10 electrons, and in case of atomic orbitals of oxygen, 8 protons are attracting 8 electrons. So in anion, here number of electrons are more. So nuclear hold or hold of nucleus on the electron will be relatively low, causing increase in the size of O minus 2. If size is more, means orbitals are away from the nucleus. If orbitals are away from the nucleus, then their energy will be higher. So respective orbitals of O minus 2 will be of higher energy, or 1s orbital of oxygen and 1s orbital of O minus 2, if I have to compare, then 1s orbital of oxygen will be with low energy because oxygen has 8 protons, 8 electrons, good nuclear force, and therefore energy is low. In case of O minus 2, number of electrons are more, so net nuclear force is less, so energy is higher. Those non-bonding orbitals are not represented. I am starting discussion from 2s orbitals. 2s orbitals are with symmetry sigma, therefore they will result two molecular orbitals, one bonding, that's a sigma 2s, and other antibonding sigma star 2s. Here, energy of 2s orbital of O minus 2 will be higher. Average energy we will consider, and from the average energy of 2s orbital of oxygen and 2s orbital of O minus 2, decrease or increase of bonding or antibonding can be understood. General approach to MOT that I am discussing. About the 2p orbitals, 2p orbital is a cluster of 3. It is a triplet. It has 3 orbitals, 2px, 2py and 2pz. Z orbital is along internuclear axis and that has sigma symmetry. It is shown by yellow coloration. The 2pz orbital of oxygen will interact with 2pz orbital of O minus 2 to produce strong interaction. That's a sigma interaction. To generate two molecular orbitals as per LCAO principle, one bonding, we represent it by yellow colored sigma 2pz, and other antibonding, It is represented by yellow color sigma star to pz. Interaction between them is represented by purple color. That's a sigma interaction. It's a strong interaction. More overlap is there. S value, overlap integral will be more positive in case of the bonding orbital, and it will be more negative in case of antibonding to pz orbital. Here, increase in energy of antibonding orbital and decrease in energy of bonding orbital we are measuring from average line, average energy of 2p orbitals of oxygen and average energy of 2p orbitals of O minus 2. Other set of orbitals 2px and 2py, they are perpendicular to internuclear axes and they will interact laterally. And we say those are of symmetry pi, and pi is a lateral overlap because of that. And lateral overlap is a weak interaction, weak overlap, and because of that weak interaction, the decrease in energy of pi to px and pi to py bonding orbitals will be relatively low compared to decrease in energy of bonding sigma orbital, that's a sigma to pz. Increase in energy of antibonding pi star to px and pi star to py will be relatively low compared to increase in energy of bonding sigma star to pz orbital. So now energetics for the molecular orbital is sigma to s, then sigma star to s, then sigma to pz, then pi to px is equal to pi to py, then pi star to px is equal to pi star to py, and last sigma star to pz. If you see oxygen, 8 electrons are there, 2s2, 2p4, outermost electronic configuration. In case of O minus 2, oxygen will take 2 electrons and then will form O minus 2. So in p orbital, just pay attention. There how many electrons are there? 6 electrons are there. So what is the electronic configuration for O minus 2? It is 2s2, 2p6. Orbitals from right side compartment from O minus 2 are of higher energy than the orbitals of left side compartment, that's of oxygen. If you read the diagram carefully, bonding orbitals will be more towards the atomic orbitals of oxygen, and antibonding orbitals are more towards atomic orbitals of O minus 2. So bonding orbitals will be with more contribution of oxygen and antibonding orbitals will be with more contribution of O minus 2. Outermost electrons are in antibonding pi star to px and pi star to py. Pi star to px and pi star to p orbitals are antibonding orbitals. They are near to orbitals of O minus 2. Means if chemical property dealing with the outermost electron, then more contribution for that property, more responsibility for that property will be of O minus 2. That's our anion, oxo ion. Let us understand the distribution of electrons. First 4 electrons will go in the inner non-bonding orbitals, K, K. First K that I am seeing, that will be the first shell from oxygen atom, low energy. Comma, second K should be there. That's a K shell from the O minus 2 ion. Then sigma 2s 2 electrons, sigma star 2s 2 electrons. So here now 8 electrons over. Ninth electron will enter in sigma 2pz, 10th in sigma 2pz. 11th electron will enter in pi 2px, 12th electron in pi 2py, 13th in pi 2px, 14th in pi 2py. Here we are following Horn's law of maximum multiplicity, Pauli's exclusion principle and Boole principle for energy level sequence. 15th electron will enter in pi star to px, 16th in pi star to py, 17th in pi star to px, 18th in pi star to py, and sigma star to pz will be with no electrons. How can we find bond order? Bond order is equal to number of electrons in bonding orbitals minus number of electrons in antibonding orbitals divided by 2. 8 electrons are there in bonding orbitals. How? In pi to px, pi to py, sigma to pz 6 electron and sigma 2s 2 electrons. 6 electrons are there in antibonding orbitals. How? Sigma star 2s 2 electron, pi star to px, pi star to py 4 electrons. So 6 electrons. 8 minus 6 divided by 2. Answer is 1. So 1 bond is present in O2 minus 2. For oxygen, 2 bonds were there. Now bond is 1. Bond order decreases by 1 because the 2 electrons are added in antibonding orbitals. How many unpaired electrons are there? 0. And because of no any unpaired electron, it is diamagnetic in nature. Let us understand the representation of its electronic configuration. See the electronic configuration. K, first K, that is the shell from O, comma means energy difference is there with the second K. That is of higher energy. That's the K is a shell from O minus 2. Each has 2 electrons. Total 4 electrons are there in those bonding orbitals. By white color, bonding, antibonding orbitals are represented. By white color, number of electrons in bonding orbitals are represented, and by yellow color, electrons in antibonding orbitals are represented. Sigma 2s, 2 electrons. The next energy level, sigma star 2s, 2 electrons. Next bonding orbital, sigma 2pz, 2 electrons. Afterwards, bonding pi orbitals, pi to px and pi to py, they are of same energy. What term we use for the same energy orbitals? Yes, degenerate. Pi to px and pi to py are degenerate orbitals. Each orbital has 2 electrons. Afterwards, other set of degenerate orbitals, but antibonding orbitals, pi star to px and pi star to py. In between them, there is equal to sign. What does it signify? Their energies are same. They are degenerate. In each orbital there, how many electrons? 2 electrons. Last highest antibonding sigma star to pz orbital has no electrons. So that's the electronic configuration for peroxoanion. From that, it will be easy for us to find bond order. By yellow color, antibonding electrons are there, and by white color, bonding electrons are there. It will be easy to us at a glance to know whether unpaired electron is there or not to find the magnetism. The way of presentation should be clear to you. How increase in energy is represented, separation by comma. That's the main intention to present this electronic configuration in front of you. Now students, many molecules and ions we have discussed, electronic configuration also we have practiced. Separate videos are prepared in order to repeat the things, in order to digest the thing properly. As a homework, simple questions. What is the bond order and magnetic property of peroxide ion, that ion which we discuss? You have to write it in the comment box. Bond order number you will write, and for magnetism you will mention whether it is a paramagnetic or diamagnetic. I am waiting for your answers.
Yes, because of the charge beared by the ion, the energy levels of the respective orbitals changes. Accordingly, contribution of those orbitals to molecular orbital changes. So if that ion is with the negative charge and who is playing the more role, that concept will be clear. Who has more contribution, and this will be the more clear when we will study heteronuclear diatomic molecules next year. And you come across that if electron is added in antibonding orbital, for each electron bond order will decrease by 0.5. In case of O2 minus 2, 2 electrons you have added. So bond order compared to oxygen will decrease by 0.5 into 1. So bond order is 1 for the O2 minus 2. Magnetic property, diamagnetic. We understood the importance of molecular orbital theory to explain the formation of molecule, molecular ion and the bond orders. Next year we are discussing heteronuclear diatomic molecules and polynuclear species, but this study is a base for you. So keep tuned, study well. That's the preparation of next year's study. Only remember, is not important for us. Application, creativity, high level learning is important for us. Think to learn, learn to think.